Okay, so the second lecture, continuation by Rajesh Sundaresan.
Hello everyone. So I'll continue the talk started by Shiva. So what I will also do is recollect some of the things that had been done to set the context for the subsequent optimizations that I will speak about. So first, some acknowledgements. So I'm actually on sabbatical leave from IISc. I'm at Strand Life Sciences. So I'd like to thank them for allowing me to take time off to do this Sero-Survey and related activity. The Sero-Survey itself was funded by the National Health Mission. I don't know if Shiva mentioned it. So we would like to thank them. And several groups have supported many of our COVID-19 response activities, response efforts. So staff are funded by funding from these entities. So I would like to thank them as well. And these are our comrades in arms, Shiva, Giri, and a host of others from IISc, many in the Sero-Survey team and a host of others from IISc who have helped with the later optimizations that I will speak about. So let's begin with recalling what Shiva spoke about, the model. But first, we'll begin with the goal itself. So the goal was to estimate the total burden or the total prevalence of COVID-19 in the whole of Karnataka. And the way Shiva did it, or at least presented the results, was that you do it in each of those districts and then weight them. So let's actually focus on one particular district. And total burden or total prevalence is defined as past infection plus current infection. It's actually important to do this when the infection is raging, when active infection is high, because from the numbers that Shiva presented, had we done only the past infection estimation, we would have had 16.8% or thereabouts, whereas active infection was estimated to be at 12%. So the state's response when it sees a 16% IgG versus when it sees a 27% IgG plus active infection is quite different. And we felt that that was sort of a post hoc justification for the protocol that was designed. The other thing is that when you want to do both of these things, the IgG as well as the antigen viral RNA or active infection testing, you have to do different types of tests to capture these, because the IgG gives only past information. It comes up only after a certain number of days, whereas for active infection, you'll have to do a different kind of test. Same individuals, and I'll come to that a little later to highlight the importance of proper test design. Just some preliminaries on what these tests are. I said we should do different kinds of tests. So here is a particular a picture or schematic which tells what these tests are and why it's important to do multiple tests on an individual, or at least on a subset of individuals. The PCR-based test can detect small amounts of viral RNA, and it can be on for a long time. So that's this gray curve. So symptoms onset at around this time, the individual has been infected, symptoms onset, and this is the height here is the probability of detection, and on this side is the time since exposure and onset of symptoms, reference being the onset of symptoms. So it can be on for a long time, and you capture viral RNA. Your body is also responding to this virus. There are viral proteins that are generated. So the antigen test captures that. The antigen tests will tell us about active infection rather quickly, whereas the PCR-based test can return positive even though you're not showing symptoms, so to speak. And then here are two classes of antibody tests, the immunoglobulin G and the immunoglobulin M. These ones both roughly, perhaps the immunoglobulin G becomes active a little later, but this picture shows as if they come simultaneously. The point is that the IgM dies quickly, and memory of past infection to some extent is captured by the IgG antibodies. There are also other immune responses that one can mount. For example, I'm told that there are things called T-cell immune response, which we will not be able to capture if an individual had mounted such a response. However, these are so any estimate that we get as a consequence is going to be an a biased estimate on the lower side as far as these things go. But of course, as the chats and the discussion in the previous talk indicated, there is also a bias on the higher side. And as Deepayan said, all that we can give is highlight all these aspects and have enough disclaimers. But I hope that this is clear as to the antigen test and the RT-PCR test captures active infection or the presence of viral RNA. The antibody test captures information about past infection. Now, we could have possibly done the IgM as well, but the survey design was something that was already in place when we joined the group, and therefore we had to just take into account IgG antibodies, test for IgG antibodies alone. Here is another picture which sort of highlights some interesting things. So on this picture, once again, you would see symptom onset at as this reference indication. And on the y-axis, once again, is the probability of detection. But what is indicated here is samples collected from various locations. So for example, the nasopharyngeal swab and a PCR test on it is likely to capture the viral RNA much better than perhaps capturing it from the respiratory tract and so on. So in our test, what was done was there was a nasopharyngeal swab taken, there was an oropharyngeal swab taken, and for those that were administered the rat test, this would be from one nostril, for example, the nasopharyngeal. And then for the same individual, there would be 2 more samples from the other nostril and another oropharyngeal sample, and that would be for the rat, just to ensure that we capture the viral RNA. But the point I would like you to focus on is that the PCR is positive for some time. The antibody is antibody detection is good, starting from about 3 weeks from the point of exposure, or roughly about 10 days or so after symptom onset. And there is an interesting period when an individual may show simultaneous activity for antibody as well as viral RNA. And so this is something that Siva also highlighted. This was sort of the clue that told us how to model the disease states and so on. And I think there are improvements possible. Ours is just a first cut model. Okay, so with this, I'll go back to the model that Siva spoke about and a list of ideal test outcomes. It's a recapitulation, but also to highlight a certain different perspective coming from a person who has a communication engineering background. So I would like to highlight that perspective as well. So I thought it would be instructive to go through this. So each individual, as we said, could be in one of 4 different states, and the 4 disease states are 1, 2, 3, 4. So in one, the individual shows active infection, but no presence of IgG antibodies. In state 2, the individual shows IgG antibodies alone. So this is a clear indication of past infection, but no active infection. In state 3, that's the interesting state where both of these are present, IgG as well as IgG antibodies as well as viral RNA. And then in the 4th state, neither. And this could potentially include people that were actually infected but may have mounted a T cell response, but there's no way for us to detect it because we don't see active infection. We also don't see IgG antibodies. Now on this side here are the 3 tests: the antigen test, the viral RNA test, and the IgG antibody test, which I index by j equal to 1, j equal to 2, j equal to 3. And these are the 4 states. And what I have here are sort of the ideal test outcomes. So we have an ideal test outcome. So if the individual is showing active infection, the rat will be positive, the RT-PCR will be positive nominally. Of course, there are errors, and I'll come to that very soon. But the antibody test nominal outcome is negative. This is IgG antibodies only. So these 2 are negative. This is positive. Simultaneous active infection and IgG antibodies. So all 3 are 1. And in this, none of these are 1, which I sort of denote by MSJ, the notation that Siva also had in his talk. Now, from here, it is clear that if you want to detect past infection, you have to do the antibody test on an individual. And if you want to detect active infection, you have to do these 2 or one of these 2. So antibody test is essential for past infection, and one of these is essential for active infection detection. And therefore, a combination of these tests is needed on at least some subset of participants to be able to get a reliable outcome. And this will be something that we will come back to a little later in the talk. I can then write down how the noisy outcomes, the test outcomes are noisy, and I can actually model this in this particular way. So here are the 4 different states of these individuals. And let's think of these as ideal test outcomes. That is a test with no error at all. And so here is a person who is in active infection state, but no IgG, which means this is for the rapid antigen test. This one is for the RT-PCR test. This one is for the antibody test. So this individual would be positive when a person in this state would be positive. And so that's what this indicates. But on the other hand, the outcome of a test with a certain sensitivity and specificity would put the individual either at this 0, that is a negative test outcome, or a positive test outcome. So one can actually indicate this in the form of a channel, as communication engineers would say, in tandem with another channel. And this channel is a binary asymmetric channel with different crossover probabilities. And the crossover probabilities are given by the sensitivities, or 1 minus the sensitivities and 1 minus specificities. Let's do one more example. So here is an individual who's in state 3. That means he is active for both active infection as well as the antibodies. So this is for the rapid antigen test. So you'll see that the nominal outcome is 1, but then when a test is done, the outcome could be either 0 or 1, depending on the test's reliability. So just to recollect what sensitivity is, it's 1 minus the false negative rate, which is also 1 minus miss probability, depending on whether you come from communications or from statistics. Specificity is 1 minus false positive rate, which is also the 1 minus false alarm probability. The same thing can be done for the RT-PCR test, and you will notice that this part is identical to this because the RT-PCR test's ideal outcomes are exactly the rapid antigen test's ideal outcome. I'll come to some differences that could have been brought in the model, but we didn't do. But nominally, in our model, at least, these two are supposed to be identical as far as their ideal outputs are concerned. But then this noisy part it has a better sensitivity and specificity, which sort of is an indication that the channel here may be better than the channel there. But you will notice that the specificity of the RT-PCR test is a little lower than the specificity. So the ordering is not exactly correct, but nevertheless, one can guess that because of the 50% sensitivity, this is a poorer test compared to this. If you look at the IgG antibody test, it looks a little different, and that's because it's actually capturing the states 2 and 3, which is antibodies only, that's state 2, but no active infection, or simultaneous presence of antibodies in viral RNA. And that would be the one. The other two would correspond to 0. That's the noiseless part of the channel, and then there is a noisy version, which is the outcome of the test that's being done. So the summary of this, and I think this is an interesting way to put things in perspective. The outcome is actually giving some information about the hidden state, but the hidden state is like passing through 2 tandem channels, noisy channels. One is noiseless and the other one is noisy. Then the other thing that I would also like to point out is that it's possible that some of these tests may not have done, and that's the content of the next slide. So protocol nuances were things that we had to handle, and data issues were also things that we had to handle. For example, only a subset of the individuals were administered the rat. This was actually a difficult problem for us to address, and I think we have not addressed this correctly because the people that are administered the rat are the moderate risk and the high risk people. So in some sense, we are biasing the administration to that, and that has not been taken, that bias has not been addressed in our methodology. And to some extent, we wanted to undo that, or we wanted to get away from this sort of allocation. And I'll come to the later part of the talk. We'll try to address exactly this question. This was a question that was raised by, I think, Abhay, as well as some individual with initials MK. And it's an important question, and it sort of makes, hopefully, the errors are second order. Then another protocol nuance is that those who are RAT positive are not administered the RT-PCR test. This is another annoyance because now the test pattern itself is dependent on the outcome of the test. And this is also something that we wanted to avoid going forward in the second and the third rounds of the survey. Then there were data issues, and Siva highlighted these. We weren't able to get the RT-PCR results for over 1,000 plus samples because there were delays. At some point of time, we just had to say we can't wait any longer. There is diminished value for the data that we might get, and we should just go forward with whatever we have. But that also meant that we had to deal with partial data. There was partial data due to other reasons as well. IgG results from one of the hospitals. In each district, there were between 5 and 15 hospital centers. From one of the hospitals, we didn't get the IgG results at all. And we had to deal with that as well. And we couldn't match many IgG results to participants because of either entry errors. There were multiple SRFs that were entered because of the antigen and the RT-PCR, each having a different SRF. One particular SRF had to be entered, but sometimes people entered the other one, and that caused issues. There were also people from multiple districts with the same name. We saw many Manjunaths, many Yogeshas, and we didn't know how to match them, particularly when we knew that they came from different districts. But the antibody test is for 2 Manjunaths in these 2 districts, and the RT-PCR and RAT were for 2 Manjunaths in these 2 districts, and we didn't know which Manjunath had to go with which Manjunath for the RT-PCR and the antibody. And this is actually an interesting statistical question, which is something like which has something like the EM flavor, except that it's sort of a discrete matching, and perhaps the statisticians amongst us may suggest some ways to handle this in rounds 2 and 3. Okay, so that led us to the following: different test patterns for different individuals. Some because of the protocol, which were annoyances, we didn't handle them correctly, and some just because data didn't match, and this shouldn't have happened in this day and age, but that's the way things were. So for example, here is a person, individual 1, for whom all 3 tests were done. That's what this indicates, 1, 1, 1, which Siva called as a test pattern. So a test pattern is whether the RAT was done, the RT-PCR was done, or the IgG was done. So it can be indicated as T1, T2, T3, triple, belonging to the 0 or 1, 1 indicating that it was done and 0 indicating that it was not done. And you would have gotten some outcomes for that individual. But if the RAT was not done, as was the case for the low risk individuals, then we would have had 0 here and only 1 and 1. In which case the outcome is taken as NA, and these 2 outcomes would have been there. But it could also have been the case that the RAT was done, and the RAT was positive, and therefore the RT-PCR was not done, in which case there would be an NA. Or the RAT was done, the RAT outcome was 0, but we didn't receive the RT-PCR, and therefore this is also NA. We have many thousand such samples. And it could also be the case that IgG didn't come back to us, in which case this would be a blank. Test pattern would have been 1, 1 for RAT and RT-PCR, but no IgG, and therefore this is an NA. So in all 8 possibilities here and 27 possibilities here, not all of them were seen, but a large fraction of them were seen. So this is the test pattern, and this is the outcome. Now, once you write down this sort of a hidden state and the output, and 3 tests, 3 looks, or depending on the pattern, maybe you see only this look, and you don't see this RT-PCR look. So you can therefore look at the output probability, that is the observation probability, conditioned on the pattern, test pattern that is being that was being administered, or that was administered for this. And so let's go through what Siva wrote down, and eventually he wrote down the likelihood. So we'll get to that shortly. The parameter for this model, it's a parametric model. The P is P1, P2, P3 with the usual positivity and some conditions. And these are the probabilities of an individual that has been sampled being in state 1 or state 2 or state 3. Just to recollect, active infection only, no IgG. IgG only, no active infection, both. And then the last one, which is 1 minus P1 plus P2 plus P3, that's P4. That's neither active infection or nor antibodies. Assume that n individuals are sampled from the population, and we'll assume that n is small enough, and we'll also make the IID assumption, etc. N is small enough so that this IID assumption is applicable, and we'll get that the state of these n individuals is IID with probabilities P1 through P4 for these 4 different states. Then an individual n is administered a certain set of tests, and we ignore the fact that for low risk individuals a certain pattern is used and so on. We'll just take it as given, and that's a test pattern, and then a test outcome is whatever we observe on this individual. And from Shiva's slides, we can then write down the likelihood where we marginalize the hidden state. You can write this as yn and s, and then marginalize the hidden state probabilities. And this ps being a parameter, we actually get a parametric model. Shiva also indicated how to write this through an example, the probability of an output test outcome, particular test outcome, conditioned on the state of the individual and the test pattern. And that's the one that goes here. But it's also clear that how one could write this from this sort of diagram. Okay, so let's go to the next slide now. So what we then do once we write down the likelihood, so given test patterns, assume, and the test patterns we just assumed are independent of the P, which is not exactly correct, but nevertheless, we'll go with that assumption. Then the likelihood of the N participants can be written in this form, assuming independent sampling. And then Shiva mentioned that this is the logarithm of this is a concave function of P, and then you can just run the maximum likelihood estimation, some iterative procedures on it, and that's the output. So through this procedure, we were able to identify the maximum likelihood estimate, and that I will call as P hat of n. Let me just recall some classical results, which is the first one of these is consistency of the maximum likelihood estimate. So there are some regularity conditions that the score function must satisfy. The expectation of the score function with respect to a mismatch parameter must satisfy. So these are all well known, and our model satisfies this. And under these conditions, what happens as the number of samples becomes large is that the maximum likelihood estimate goes to the true estimate in probability. So that's something that we can be thankful for. And the other thing is asymptotic normality. So under some additional conditions, which is also something that are very simple, discrete, it's just a discrete model. And so these additional conditions are straightforward to verify, but I'll not go over them. A model satisfies them. We have asymptotic normality as well. And therefore, one can write down these centralized errors, multiply that by root n, and argue that they converge to this normal distribution. The mean is 0, and the covariance is given by the per sample Fisher information matrix evaluated at the parameter point P. And therefore, what one can do using this is one can look at the P hat of n as being approximately normally distributed with the true parameter as the mean. And then there is a normal, the covariance, because of this rescaling, when you take it back in, it actually appears as the Fisher information matrix per sample scaled by n. And one gets this inverse of that Fisher information matrix for the n samples together. It's inverse as the covariance matrix. With this, if you look at the estimates now, the confidence intervals are fairly straightforward. So let's suppress the n, which indicates that the number of samples. So active infection is just the estimated parameter, the first component of the estimated parameter, which is active infection only, no IgG, plus both active infection plus IgG. So this measures active infection. This measures IgG, which is P2 plus P3, and the total disease burden is just P1 plus P2 plus P3. Now you will notice that P1 plus P2 plus P3 is just a linear transformation of this estimated parameter, and therefore given that we know the asymptotic, how the variance is approximated, the covariance of P hat, the vector P hat is approximated, you can write down the variance of this straightforwardly using this quadratic formula. So U transpose the n sample Fisher information inverse U. And from this, so that's the variance. from this you can get the 95% confidence intervals, which is the estimate. So we take the sample, the estimated values as sort of the center, and then the standard error around it. So here we will just plug in the p hat, p1 hat, p2 hat, and p3 hat. So I should have put the hat here. So that would sort of give the standard error for this. And the 1.96 corresponds to the 95% confidence interval, assuming that this is actually Gaussian distributed. In response to many of the questions that were there in the first talk, which were related to bias, we inflated this by a factor of √3. That is the variance we multiplied by 3, and that's the design effect. So those were the numbers that Siva reported. Okay, now a little bit more about this Fisher information matrix. So the variance was approximately, I mentioned, U transpose the Fisher information matrix for the n samples inverse U. This is for the total prevalence or the total burden of the disease, where the U is this all one matrix. What is this NIP? One can actually write this as sum of these weighted per sample Fisher information matrices for each pattern at the parameter P. So here, so this is the WT-ITP, but the weights are essentially the number of tests that are done for test pattern T. So this is actually this is a straightforward classical result, and what we can use is the total Fisher information matrix when WT tests of pattern T were done is the per sample Fisher information matrix for that pattern T multiplied by that, and then you sum it up across all the possible test patterns. Now this is quite intuitive, because this is what is the quality. This measures the quality of the information, and that we are able to gather the variance of the estimates and so on. And as a consequence, the more of some kind you accumulate the quality according to whatever the Fisher information matrix per sample for that test pattern gives. Okay, so in all of this, in the maximum likelihood estimate that Siva gave in the confidence interval estimation, what is really new? An honest to goodness assessment would say that the only thing that is new is perhaps this picture, which basically took mapped these 4 states and then got the outputs based on these test outcomes. And then once you put this picture, everything else is straightforward, standard fare all the way. You handle, for example, multiple tests in a natural way. The likelihood is just the product of these. You can handle situations, for example, where the IgG is negative and the RT-PCR is positive. When you take this joint probability of the outcomes, it naturally enhances the information that we get, or enhances the evidence for IgG being 0 when the RT-PCR is positive, and vice versa. It also naturally handles noisy observations. The rat sensitivity is 50%, etc. And it handles partial data in a very natural way. Once the model is identified, once we get this, it's just classical maximum likelihood estimation. And I would like to point out that what this does is it is a generalization of a standard formula that is used in IgG tests alone. It's called the Rogin-Gladen formula. In that, when you do just one test, for example, the IgG antibody test, this is usually the what's called the adjusted estimate that takes into account the sensitivity and specificity. You can write it in closed form in this case, but in the more general case, we have to have a numerical procedure. So that's about what's new. Now let me go a little beyond what was done in the survey, and that is how we can go forward and improve the Karnataka survey. So in the Sero-Survey that we conducted for Karnataka, we actually lived with whatever number of test patterns we got. So we didn't control this at all. So could we have done better for the money that we spent? And so what's the money that we spent? So I'll give now an estimate of what that is. So let's look at what the cost of a rapid antigen test is. It's about 450 rupees. That's roughly about 8 euros or thereabouts. The RT-PCR test costs about 1,200 rupees. That's about 25 euros or thereabouts. And then the IgG test costs about 300 rupees. Now, the total number of these tests are given here: 11,000 RAT, 16,500 RT-PCR, 16,500 IgG, and the overall cost is about 3 crores. I'm not able to quickly calculate it and tell it in euros, but it's a significant amount of money. Um, so what we would like to do, what we would have, uh, what we'd like in round two is, are we making the best use of this money? Are we getting the maximum amount of information that we can get for the money that we spend? And that sort of poses this design problem. So here's the articulation of this design problem. Given a budget C, a cost CT for the test pattern. I'll come to the CT very soon. So maybe I'll explain it here. CT is, if I have a test pattern T, which says that do the antigen test plus the antibody test, then CT is the cost of only those two tests summed up. For an individual, for a test pattern where all three are done, CT would be the sum of all the three tests. So let's say that we are given a budget C and a cost CT for a test pattern T. How many participants should be administered test pattern T? Okay, this is a very relevant question, and here's one explanation why. So if the test pattern T, for example, is 101, what does this mean? This is you're administering the antigen test, no RT-PCR, and the antibody test. Then you would recollect that the cost of this pattern is 750 rupees. On the other hand, if you did the RT-PCR test, which is a little more expensive, and the antibody test, then that's about 1,200 plus 300, which is 1,500. So that's twice this. So for one test of this pattern, you can actually recruit 2 individuals and conduct this particular test pattern. So for the same cost, I could administer 2 first pattern tests to 2 individuals versus 1 pattern of this type to 1 individual. So how should the field epidemiologist allocate the C rupees to all these test patterns? And what's the epidemiologist's goal? What is the epidemiologist after? What's the objective function? So the following is instructive. So let's look at the simplest case. In the simplest case is, let's say that we have a budget C and we allow only one test. And this one test in the simple example is the IgG test. So through this IgG test, the only thing that you can estimate is the antibody prevalence. And let's just settle for that. The cost of this IgG test, let's call it a C of IgG. If n tests are administered, then there is a very natural estimate. You don't need any numerical procedure for this. It's just the fraction that come out positive. That estimator has a variance which is p into 1 minus p divided by n. And I'm assuming that the test is perfect. There is no noise in the test. It's a perfect test, and so you will estimate the population prevalence to be something, and its variance around this estimated value would be p into 1 minus p divided by n. But the cost of these n tests is n times this, which is less than or equal to c, which means that you can't do more than capital C divided by the cost of one single test. And so to minimize this variance, which is sort of the objective that I'm suggesting, what one needs is an n which is as large as possible. So you take n is equal to whatever is the largest possible, which is the total cost divided by the cost of one test. So thus the minimum variance looks like this: p into 1 minus p into cost of one test divided by the budget that you have. And you can ask, if you don't know what the p is, you can do a worst case design where you optimize, you maximize for the p. And we know that that's 1/4, and so this would be the worst case design. If you have some side information, for example, when we go into the round, in the second round, we know that p might be bigger than or equal to, let us say, 0.3, in which case you can optimize over that alone. So this suggests some interesting things, which is highlighted here. How much accuracy can our budget of C rupees buy? So here is C rupees, and here is the variance that I have plotted. And it has this inverse relationship. And there is a constant, and that constant depends on where we are, in which stage of the pandemic are we in. And if a lot more people were infected, then this would move back and forth, with the worst possible value being at p is equal to 1/4. Okay, so I hope this is clear. So this is in the simple case, but it's quite illustrative because for one, it suggests what our epidemiologist's objective should be. And two, it also poses the next question or enables us to articulate the next question, which is back to our design problem. Here is our second goal. Given a budget C and cost CT for test pattern T, how many participants should be administered this particular test pattern in order to minimize the variance of the total disease burden we had. So our objective has now been clarified. It's the variance of the total disease burden. So from three parameters which I'm estimating, I'm settling for just one parameter, and I'm asking to minimize that. One could have a multiple objective criterion also, but here we take this particular single objective and we try to optimize that. And the other thing that we also ask is somehow get this test pattern to be optimized. So we will actually not do this on the fly, but we will try to fix this upfront so that some of the um, uh, uh, likelihood writing issues or the way in which we have approached this particular problem could be taken care of. So here is a mathematical formulation. So this is the per sample Fisher information when pattern T is used. WT of them are used, and then you sum it up over T. So this is the overall n sample Fisher information matrix that's being used when the design is to do WT tests of type T for each of the T. And then the variance is given by this U transpose Fisher information matrix inverse U. And what we would like to ensure is that the cost is less than or equal to C and the WTs are all positive. So if you're doing WT tests of type T or pattern T, that pattern costs CT, and so this is the overall cost that better be less than or equal to C. So this is actually fairly straightforward to solve because I'll just do it in words. You can bring the C down here and then sort of write this as a probability vector, which I'll call as another variable VT. So WTCT by C is something that sums to less than or equal to 1. And it's also natural to expect that you should use all the budget that's available. So we can even make it sum up to 1. And the fractions can then, so that WTCT by C can then be interpreted as how much of the budget C, what fraction of the budget C am I allocating for test pattern T. Once you do that, once you do this change of variable, you can bring that WTCT by C in here. And so that means I multiply by CT and divide by CT. And so, and also divide by C and multiply by C. And that capital C can be pulled out. You can write this as our new variable, and we have an IT divided by CT. And so you'll recognize that it's an optimization problem that is independent of C, and then the C, capital C, the budget comes out as a C inverse. So that's summarized here. And this such a design is called a C optimal design. So let the vector, so here's a result that we can prove. So here is our C independent optimization that we come up with in terms of the fractions of the budget being used for each of those test patterns. And if you use that pattern, the information that you get is ITP, but it is normalized by the cost of that. So a test which is extremely expensive, very good, but extremely expensive, is something that will be valued somewhat less by this reweighting. And what we are trying to optimize is this overall number, and the overall budget comes outside. So let V star optimize this C, that is budget independent optimization problem, which is very similar to the original one, except that the Fisher information matrices for each test pattern is normalized by the cost of that pattern. And let's say we have that to be V star. Then the optimal allocation is actually fairly straightforward. It's just VT star divided by CT multiplied by capital C. So that gives us the number of tests of type T that we would do. Also, the minimum variance goes like this. It depends on our test optimal test allocation, but then the budget comes down as A of V star divided by C, where A of V star is the value of this objective function. So to summarize, how much accuracy can the budget of C rupees buy? It's exactly like this. If you use a budget allocation fraction of rupees for test pattern T given by this VT, then you have a number A of V, which is just this quadratic form, and then evaluated at averaged according to VT, and then the prevalence is P, and then divided by C. So if you increase your budget, your variance will come down. So that's exactly the same as before. And then you will also see that there is now an additional variation in addition to shifts according to the disease prevalence. Things also depend on your design. So one could how to optimize this is what the previous slide gave. So here are some numerical examples just to illustrate the ideas. I have, I think, another 5 more minutes. So I'll try to wrap up soon. So then some numerical examples. So let's say that we have these test costs. These were the ones that I had highlighted earlier. One can solve this optimization problem. And if you do it, this is what we get. If the RT-PCR cost was indeed 1,200, then what we see is that the optimal strategy is actually not to do any RT-PCR. This is too expensive. Even though it's a good test, it has higher sensitivity and specificity. It's too expensive. And one must settle for just the IgG test on some fraction of the individuals, and only RAT and IgG tests on a certain other fraction of the individuals. And the number of tests that you should administer are in the ratio 1:24. So there are, for every individual who's administered only the IgG test, there are 24 individuals who should be administered the RAT and the IgG. Now, if it so happens that the RT-PCR test cost comes down and is about 1,000 rupees, then the RT-PCR test becomes competitive. And the right thing to do in that case is not to do any rapid antigen test. And so there is a fraction of individuals who are administered only the antibody test, and another fraction who are administered only the RT-PCR test and the IgG test. The point being that in this situation, there is no rapid antigen test, and in the other situation, there is no RT-PCR test. So this sort of tells how to optimally allocate the budget to minimize the variance, which seems like a natural objective in this case. Now, I want to give 2 extensions which sort of also address some of the questions that were raised in the previous talk. And those questions are related to, the first one is, of course, worst case design. So we saw that when you had only one test, we had a P into 1 minus P dependence coming into the picture. And if you optimize for that, then you would get a worst case design. Can we do a similar worst case design here? And it turns out that yes, you can. And in order to enable that, you have to demonstrate that this function, which is the cost independent objective function that depends on the fraction allocated for each test, and also the parameter P. So this cost independent factor is convex and concave in the right parameters. So for example, the person that's optimizing is trying to choose a test pattern that minimizes this variance, and so it's convex in that variable. In that variable. On the other hand, if you're trying to the worst case maximizes the P, it's concave in that particular variable. One can show that, and therefore one can view this as a game which is convex and compact in the right variables, provided the sets over which your the players can choose these values are also compact and convex, and the game therefore has a value, and that gives us a worst case design. So this is another extension. This is one extension to the previous result. There's another one that we can do, which is sort of taking a cue from one of the observations that Siva made, that the rat was more sensitive on people that show symptoms than on people that don't show symptoms. So it was 68% or 67% sensitive on symptomatics versus 47% sensitive on asymptomatics. That's actually a valuable information, because then you can prioritize your antigen tests on those that have symptoms. So how best do you do this? And this is something that you can do on the field. As you see participants come in, you can ask, are they showing symptoms or not? And then based on the factors that you see for this particular individual, if they are symptomatic, you can administer a certain test pattern. If they are not symptomatic, you can administer a certain other test pattern. And one can come up with an optimization problem for that as well. And one can solve that as well. I'll not go into the details of this. So what the outcome suggests is that you should use RAT with a higher frequency on those who are symptomatic than on those who are asymptomatic. And here is the methodology to solve this. It's actually breaking up the problem into two parts. One for allocation on those that are symptomatic and another for those that are asymptomatic. And a priori, uh, we assume information about what fraction are symptomatic and what fraction are asymptomatic. In practice, this may not be available, but at least for this particular problem formulation, we assume that it's available. Let me now summarize. So we demonstrated how to optimally allocate test patterns to minimize the variance. This is not something new. It's what is called C-optimal design. And all that we are proposing is that we use the C-optimal design to come up with how many tests of each pattern. With this, we can identify what's the accuracy that our budget can buy, or we can also reverse the way in which we think about this and say that if we want this much amount of accuracy, what's the budget that we need? So we could do that as well. Now, the qualitative results are such that the test proportions don't change. It's just if you have more budget, what you should do is you should just proportionately increase the number of tests of each pattern. Now, this is the C-optimal design is actually quite classical, or at least a variant of that is quite classical. There is a paper by Chernoff in 1953 where Chernoff looks at the inverse Fisher information and he tries to optimize the trace, which is another scalarization of a vector objective of three variances for the three parameters. And Chernoff gives the answer for that. But the more appropriate one for us is this U transpose Fisher information inverse U, which is called a C-optimal design. Now, two other points I want to make is that our goal in doing this optimal design is only to minimize the estimation of the disease burden and its variance. So the goal is that it's a somewhat insensitive objective, but in practice, there may be many additional goals that may warrant the use of RAT on account of its point of care usability. So you know about an individual's status when the outcome is positive, then and there, and you can essentially give care, or you can ensure that that person gets the care he or she needs at the point of care, point of test location. So the RAT actually serves several other purposes. But if we are blind to this and we want to just minimize the variance of our estimate, then this is a good design. So with that, I will stop. Thank you.
Okay, so question time. So any questions?
Maybe I'll ask Rajesh to comment on this. Rajesh, we discussed this many times, right? That is, by sensitivity, can we lower sample size and do something else rather than do it this way in terms of the criteria? So Manju asked the question. I replied. You can reply more.
Can you repeat the question?
So,
I mean, this optimization, it was not clear what it was over. My question, okay, maybe what Siva, you can tell. Maybe that is better. No, my
ask the question. Go ahead.
No, my question was whether your optimization. I mean, RT-PCR, if it's the better test, you could also reduce sample size and only do RT-PCR. So there was some calculation you showed about if you reduce from 1,200 to 1,000.
Correct.
It's a different thing. So I'm asking, yeah.
And that is exactly what we are trying to answer here. So when we look at this WT for each of the patterns, it's telling, so for example, let's look at a test pattern which is only RT-PCR and another test pattern which is only RAT, the rapid antigen test. So these WTs for each of these entities, test patterns, will tell us how much of this should we run and how much of the other should we run. And it turns out that, and that's exactly what this one is also suggesting, when you actually do this, when the RT-PCR test reduces to 1,000 rupees, you should do only the RT-PCR and the IgG tests in the ratio 4:3. That means there are fewer tests now. The number of participants you will recruit is lower because the RT-PCR plus IgG is about 1000 plus another 300, 1300.
No, this has the costs of the test there, but where is the sensitivity in this analysis?
So the sensitivity comes from the Fisher information here. So if you look at this ITP, the ITP, so let me go back to this formula here. So there is this probability of, so you see this model, parametric model, which took the parameters P. Here, the sensitivities will all appear here in the probability of a test outcome conditioned on the test pattern and the disease state.
Okay.
Or you look at this. So that this particular Q of Y given TS, which is also something that you can glean from this diagram, that captures the sensitivities and the specificities. And the Fisher information matrix is actually for this model with the state hidden and the outputs being noisy.
Yeah. Okay.
Okay. Yeah. I hope
I'll just sort of clarify one last point that he raised also. That is, the sample size also automatically determined by the cost and the reduction in variance. Right?
That is correct. Yes.
Aditya had a question. I don't know if it's answered or not. Aditya?
No, it may have been answered. I was just curious to know, was this the methodology to arrive at the n equal to 432 samples number?
Yes. So if you actually go back to this number here, you see the P into 1 minus P divided by N. So they wanted, the 432 was also a number that was decided before we got into the act. So they assumed a P of 10% and then said that I want a margin of error of less than or equal to 0.05. So that margin of error, you take this square root and that's one standard error. So they wanted that to be less than or equal to 0.05. And that margin of, so there was a 95% confidence also that was required. So that would give a 1.96 factor. And then additionally, there was a design effect, which was 3. So all of those put together would give 144. Would give
This question was it based on the cost? No, it was just based on this number.
It was just based on this number. Yes. It was based on an argument that basically looks at this and says that I need this to be less than 0.05 square. So what's the
Sure. So maybe in future rounds, are you considering bringing in more explicitly the costs to come up with better efficient sample numbers?
That is precisely why we have attempted to solve this problem. So in round 2, it is our hope that depending on the cost of the RT-PCR, we will either go with this or with this one. Which actually is an enormous simplification in terms of actually getting more data through, because when you do only the antigen test alone, or when you do only the RT-PCR test alone, it simplifies the testing procedure. It also means that there are, so when you do 2 tests, there are 2 SRFs that are generated. And we lost a lot of samples because everyone was supposed to use the RT-PCR's SRF, but many use the RAT's SRF. But another person would write the RT-PCR's SRF and we couldn't match them. So at least those issues we would avoid if we can go with this simplified testing procedure. So it has benefits other than just optimal testing.
Rajesh, this also does the following, right? That it'll uniformitize this test across these groups.
Correct. Yes, that is correct. Which would address another question that a gentleman by the name MK and Deepayan had asked. Deepayan or Abhay, I think.
MK is Manjunath.
Oh, okay.
Well, there is a, okay, so was that answered? Are there other questions?
Can I ask one last question, Aditya?
Yeah, go ahead.
Yeah. So Rajesh, so since you said the C-optimal design, I mean, this was only focused towards only one vector U, right? Like one particular linear function of the parameter.
That's correct.
Is it possible to do it for multiple in a worst case, like some G-optimal? I think it's called G-optimal or something. Not sure.
It is possible to do. There are many design criteria that people have used. I mentioned the trace criterion of Chernoff's. We have to go back to the epidemiologist and ask him or her what the ultimate goal is. So this is a proposal that we will take. And we will also try to do the following, which might actually come back to complicating matters. and that is to handle the symptomatics and the asymptomatics somewhat separately. But we'll try to use only this information and nothing else.
So I have a question if I have time.
Yes, go ahead, Deepan.
This is okay. So this is not regarding this current discussion, but Shiva mentioned some regression models that you did,
Yes.
and I think you haven't gone into the
yeah, maybe I can
benefits of
quickly
that.
describe that regression model. Let me go
No,
back to
that's fine. Maybe you could, but my question was slightly different. So this the different rates for the rat sensitivity from these asymptomatic and symptomatic groups, that must have come out from that, right?
Correct. So no, it didn't come out from that particular one.
Or is it
Although we
just a sort
used
of very crude
yeah,
thing?
we did a cruder estimate. So I'll tell you exactly what we did. We actually looked at that estimate. Looked at the symptoms. We also looked at all those individuals who were PCR confirmed. And from among those, we looked at all those for whom the the rapid antigen test was conducted. And then we just did a simple crude estimate. I think this estimate can be improved based on this modeling strategy that you're suggesting. But the 68% and 57% was a last minute addition to our work, where we thought, okay, this is something that might be important. Let's quickly estimate it. And we did this crude estimate. But yes, we could try a better estimate. Good suggestion.
Okay, I was just thinking of some ideas about that. I'll email you after the talk.
Sure.
Yeah.
More questions, comments? Okay, if not, so maybe everyone can unmute themselves. So